Hello there. I'm so glad you found your way here tonight. Wherever you are in the world tonight, allow yourself to settle into this shared moment of stillness. Let the noise of the day soften. Let your thoughts grow quiet, like clouds drifting slowly across an evening sky. Imagine standing at a window, watching the first drops of rain begin to fall. The air carries the faint scent of petrichor, that ancient smell of earth after a storm. Above you, the sky shifts in shades of gray and silver, alive with invisible currents of wind. Tonight we journey through the quiet wonders of weather. There is no test waiting at the end. No rush. No urgency. Just the slow unfolding of the atmosphere's most extraordinary secrets to carry you gently towards sleep. We will explore how clouds can weigh more than mountains, how lightning burns hotter than the surface of the sun, how storms shape landscapes and guide the migrations of countless creatures, all of it waiting to be whispered into the stillness. Tonight, let's drift off together, while exploring over 100 soothing facts about weather. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable forces that shape our skies. Either way, this space is for you. There is something deeply calming about contemplating the wonders of weather. Every cloud, every raindrop, every gust of wind carries within it a story as old as the earth itself. You are part of that story. The rain that falls tonight has cycled through oceans and rivers for billions of years. The air you breathe has been stirred by storms across every continent. The very water in your body has been clouds, has been snow, has been the mist rising from ancient seas. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow. And let the weight of the day drift away like morning fog lifting from a quiet valley. Weather is patient beyond measure. Clouds form and dissolve in rhythms older than any civilization. Storms gather and pass like slow breaths across the land. Rain falls, evaporates, and falls again in cycles that have repeated for eons. And yet, within all that slowness there are sudden bursts of wonder. Lightning that splits the sky in an instant. Tornadoes that spin with impossible fury. Hurricanes that carry the energy of entire nations. Tonight, we will wander through this magnificent world. We will meet storms that have raged for centuries, and raindrops that hold secrets of physics and beauty. And we will uncover truths about weather that may surprise even the most curious minds. But there is no hurry. The sky has been changing for billions of years. It can wait a little longer while you rest. Let us begin with the immense power hidden in clouds. A single storm cloud can weigh more than 1 million elephants. The water suspended within a typical cumulonimbus thundercloud can amount to hundreds of thousands of tons, yet this enormous mass floats effortlessly above our heads. Each tiny water droplet is light enough to be held aloft by rising currents of air, but when you add together the billions of droplets in a mature storm cloud, the total weight becomes staggering. Scientists have calculated that a large thunderstorm can contain more water than flows through the Thames in a day. The cloud remains airborne because its weight is distributed across an enormous volume, with the upward push of warm air balancing the downward pull of gravity. When the droplets finally grow too heavy for the air to support, they fall as rain or hail, releasing that hidden weight back to Earth. The next time you watch storm clouds building on the horizon, remember that each dark tower holds the weight of mountains invisibly suspended in the sky. Raindrops are not teardrop-shaped, but more like tiny hamburger buns. The classic image of a teardrop falling from the sky is one of the most persistent myths about rain. In reality, raindrops begin their journey as nearly perfect spheres, held into shape by surface tension that pulls the water into the smallest possible surface area. As they fall and grow larger, air resistance pushing up from below flattens their undersides, creating a shape that scientists describe as resembling a hamburger bun or a bean. Very large drops become so distorted by air resistance that they eventually break apart into smaller droplets. The transformation happens in fractions of a second, invisible to anyone watching from below. Small raindrops, those less than a millimeter across, retain their spherical shape throughout their fall. Understanding the true shape of raindrops has practical applications in radar technology, which relies on knowing how drops scatter radio waves as they tumble through the atmosphere. The smell of rain comes from ancient oils and cosmic particles. That distinctive earthy fragrance that rises from the ground during the first moments of rainfall has a name: petrichor. The scent originates partly from oils released by plants during dry periods, which accumulate on rocks and soil, and are then released when raindrops splash against the surface. But the smell also carries something far more ancient. Certain soil bacteria produce a compound called geosmin, which human noses can detect in concentrations as low as a few parts per trillion. When rain disturbs the soil, tiny aerosol droplets carry geosmin molecules into the air. Some scientists believe our sensitivity to this smell may be an evolutionary adaptation, helping our ancestors locate water sources after dry spells. The cosmic connection comes from particles in the atmosphere that seed raindrops, some of which drift down from space. Every breath of petrichor connects you to both the local Earth and the distant universe. Clouds both warm and cool the planet depending on their type. Different types of clouds have dramatically different effects on Earth's temperature, making them crucial players in the global climate system. High, wispy cirrus clouds are thin enough to let most sunlight through to warm the surface below, but they trap outgoing heat like a blanket, creating a net warming effect. Low, thick stratocumulus clouds act more like mirrors, reflecting incoming sunlight back into space and cooling the region beneath them. The balance between these warming and cooling effects is one of the greatest uncertainties in climate science. If warming temperatures create more high clouds, the warming could accelerate. If they create more low clouds, the warming could slow. Clouds form and evolve so quickly that even the most powerful supercomputers struggle to model them accurately. The fate of our climate may ultimately depend on which type of cloud predominates in a warming world, a question scientists are still working to answer. Fog can become so thick you cannot see your own feet. In the densest fogs, visibility can drop to just a few meters or even less, wrapping the world in an impenetrable white blanket. Fog is simply cloud that forms at ground level, created when air near the surface cools enough for its moisture to condense into countless tiny suspended droplets. Advection fog forms when warm, moist air moves over a cold surface, which is why coastal cities often experience thick fogs when marine air rolls over chilly waters. Radiation fog develops on clear, calm nights when the ground radiates away its heat and chills the air above it. The world's foggiest places experience more than 200 foggy days each year, creating eerie landscapes where sounds are muffled and familiar places become strange. Before modern navigation technology, sailors dreaded fog more than storms, knowing that the white void could hide rocks, icebergs, or the shapes of approaching ships until it was too late. Some clouds form at the very edge of space. Noctilucent clouds glow with an ethereal blue-white light, visible only during the deepest twilight, hovering at altitudes of around 80 kilometers, where the atmosphere fades into the vacuum of space. These are the highest clouds on Earth, formed from ice crystals condensing onto particles of meteoric dust that constantly rain down through the upper atmosphere. They were first observed in the 19th century, and may be becoming more common as methane from human activity rises and oxidizes into water vapor at extreme altitude. Noctilucent clouds are visible only when the sun has set at ground level, but still illuminates these extreme heights, creating a ghostly shimmer against the darkening sky. Scientists study them as sensitive indicators of conditions in the mesosphere, a region too high for weather balloons and too low for most satellites. Watching noctilucent clouds is watching the boundary between Earth's atmosphere and the cosmos itself. Lightning is hotter than the surface of the sun. A lightning bolt can reach temperatures of around 30,000 degrees Celsius, roughly 5 times hotter than the visible surface of the sun. This extreme heat is concentrated in a channel only a few centimeters wide, making lightning one of the most intense natural phenomena on Earth. The temperature spike happens so quickly, in just a few millionths of a second, that the air along the lightning channel has no time to expand gradually. Instead, it explodes outward in a supersonic shock wave that we hear as thunder. The intense heat briefly ionizes the air into plasma, the same state of matter found in stars. Despite lasting for only a fraction of a second, each lightning stroke releases enough energy to power a household for several days. The brilliant white light we see is the visible signature of air, being superheated beyond anything found naturally on Earth's surface. The sound of thunder is air exploding from sudden heat. Thunder is not the sound of lightning itself, but rather the sound of air being violently superheated and then rapidly cooling. When lightning passes through the atmosphere, it heats the surrounding air so quickly that the air expands faster than the speed of sound, creating a shock wave. This shock wave starts as a sharp crack near the lightning channel and then spreads outward, diminishing into the rumbling we associate with distant storms. Because light travels nearly 1,000,000 times faster than sound, you see lightning almost instantly, but hear thunder only after a delay. Counting the seconds between the flash and the rumble, and dividing by 3 gives an approximate distance in kilometers. Close strikes produce sharp, terrifying cracks, while distant lightning creates the long, rolling rumbles that echo across valleys and hills. Every thunderclap is an atmospheric explosion in miniature. Lightning can strike the same place more than a dozen times. The popular saying that lightning never strikes twice is entirely false. In fact, some locations are struck repeatedly during a single storm. Tall structures like skyscrapers and radio towers are particularly vulnerable because their height provides an easier path for the electrical charge seeking the ground. The Empire State Building in New York is struck by lightning around 24 times each year, with some storms hitting it repeatedly within minutes. Lightning follows the path of least resistance, and once a channel of ionized air forms between cloud and ground, subsequent strokes often follow the same pathway. Some people have been struck by lightning multiple times throughout their lives, and survived to tell the tale. Scientists use specially instrumented towers to deliberately attract lightning, allowing them to study its properties in detail. Far from being random, lightning is drawn to certain places by the physics of electricity seeking ground. Lightning strikes can turn sand into glass sculptures called fulgurites. When lightning strikes sandy ground, the intense heat fuses the sand grains together almost instantly, creating hollow glass tubes called fulgurites. These fragile structures follow the path the lightning took through the soil, sometimes branching into delicate root-like formations that can extend for several meters. The temperature required to melt sand into glass is around 1700 degrees Celsius, well below what lightning delivers, so the transformation happens in an instant. Fulgurites are fragile and often crumble when dug from the ground, but intact specimens reveal beautiful patterns formed by the lightning's passage. Ancient peoples sometimes collected fulgurites as sacred objects, not knowing their true origin, but recognizing their unusual nature. Scientists analyze the gases trapped inside fulgurites to learn about atmospheric conditions at the moment of the strike. Each fulgurite is a frozen recording of a lightning bolt that struck that exact spot, preserved in glass for centuries. Ball lightning has been seen glowing inside aeroplanes. Ball lightning is one of the most mysterious and least understood atmospheric phenomena, appearing as a glowing sphere that floats through the air for several seconds before vanishing. Witnesses have reported seeing ball lightning pass through walls, roll along floors, and even appear inside aircraft during thunderstorms. Its behavior defies easy explanation, as it seems to move independently of wind and gravity. Scientists have proposed numerous theories to explain ball lightning, from burning silicon vapor to small-scale plasma vortices, but no single explanation has gained universal acceptance. The phenomenon is so rare and unpredictable that it has been difficult to study systematically, leaving researchers to rely largely on eyewitness accounts. Some witnesses report a slight hissing sound, while others describe the orbs as completely silent. Ball lightning remains one of those tantalizing mysteries that reminds us how much the atmosphere still hides from our understanding. There is a storm in Venezuela that has produced lightning for centuries. At the mouth of the Catatumbo River, where it meets Lake Maracaibo in Venezuela, a unique atmospheric phenomenon creates almost continuous lightning for up to 300 nights each year. This ceaseless electrical display, known as Catatumbo lightning or the everlasting storm, has been documented for centuries and once served as a natural lighthouse for Caribbean sailors. The phenomenon occurs because warm Caribbean winds collide with cool air descending from the Andes, creating perfect conditions for the endless generation of thunderstorms. The region may produce more lightning per square kilometer than anywhere else on Earth, with the storm visible from hundreds of kilometers away. Local legend attributes various supernatural powers to the lightning, while scientists have studied it as a unique laboratory for understanding storm electrification. The Catatumbo lightning generates significant amounts of ozone, and has been proposed as one of Earth's greatest single regenerators of the ozone layer. Standing beneath this storm is witnessing a display of atmospheric electricity that has not ceased for as long as anyone can remember. Snowflakes can fall at vastly different speeds depending on their size. The speed at which a snowflake drifts to Earth depends on its size, shape, and the density of the air it falls through. Tiny ice crystals may take over an hour to fall from cloud to ground, floating and spinning almost weightlessly in the still air. Larger, denser snowflakes can reach the surface in just minutes, falling at speeds of up to 2 meters per second. The most delicate, branching snowflakes have a larger surface area relative to their weight, which creates more air resistance and slows their descent. In calm conditions, snow falls nearly straight down, but even gentle winds can carry flakes sideways for considerable distances. Falling through warmer layers of air can partially melt snowflakes, causing them to clump together into those large, wet flakes that characterize spring snowstorms. Watching snowfall is watching countless tiny crystals, each with its own terminal velocity, drifting through the atmosphere on paths determined by physics and chance. Some snowflakes grow wider than a coin under the right conditions. Under specific atmospheric conditions, snowflakes can grow to remarkable sizes, with some specimens measuring several centimeters across. These giant flakes typically form when temperatures hover just below freezing and humidity is high, allowing crystals to accumulate additional ice as they fall. The largest snowflakes on record were reportedly observed in Montana in 1887, with witnesses describing flakes as wide as dinner plates, though such claims are difficult to verify. Most snowflakes are far smaller, just a few millimeters in diameter, but even these contain astonishing structural complexity. The precise pattern of each snowflake depends on the exact temperature and humidity conditions it encounters during its formation and descent. No two snowflakes are likely to be truly identical, given the countless possible combinations of conditions each one experiences. The simple act of catching snowflakes on a dark sleeve reveals an endless gallery of frozen art. Blizzards can reduce visibility to almost nothing. In the most severe blizzards, visibility can drop to near zero, as driving snow fills the air so densely that the world disappears into a white void. The official definition of a blizzard requires sustained winds of at least 56 kilometers per hour, combined with blowing snow that reduces visibility to less than 400 meters for at least 3 hours. In the most extreme cases, what meteorologists call ground blizzards, the wind picks up already fallen snow and whips it into impenetrable walls of white. Travelers caught in blizzards can become disoriented within meters of shelter, unable to see landmarks or even tell which direction is up. The wind chill during blizzards can push effective temperatures far below zero, making exposed skin vulnerable to frostbite within minutes. Throughout history, blizzards have stranded travelers, collapsed buildings, and isolated communities for days or weeks at a time. The quiet world that emerges after a blizzard, blanketed in deep snow and perfect silence, hides the fury that created it. Hailstones grow in perfect layers like the rings of an onion. When you slice a large hailstone in half, you reveal a beautiful pattern of alternating clear and cloudy layers, each one recording a journey through the storm cloud. Hailstones begin as small ice pellets caught in the powerful updrafts of a thunderstorm, carried high into freezing regions where they accumulate additional ice. Each pass through layers of different temperature and humidity adds another coating, with some layers freezing so quickly that air bubbles are trapped inside, creating the cloudy appearance. The clear layers form when freezing occurs more slowly, allowing air bubbles to escape before the water solidifies. A hailstone may cycle through a cloud dozens of times before growing heavy enough to fall to earth. The largest hailstones can contain over 20 distinct layers, each one a record of a few seconds spent at a particular altitude. Cutting open a hailstone is reading a story written in ice about its wild ride through the storm. The largest hailstone ever recorded was nearly the size of a volleyball. In July 2010, a hailstone measuring nearly 20 centimeters in diameter and weighing almost a kilogram fell during a severe thunderstorm in South Dakota, setting a world record for the largest ever documented. Hailstones this size require extraordinarily powerful updrafts to keep them aloft while they grow, with wind speeds exceeding 100 kilometers per hour. The impact of such massive hailstones can punch holes through roofs, shatter car windshields, and injure or kill people and animals caught in the open. The South Dakota stone was carefully preserved and measured by the National Weather Service, the though it had lost some mass to melting before official measurement. Throughout the world's hail-prone regions, large hailstorms cause billions of dollars in damage each year to crops, buildings, and vehicles. The energy required to suspend and grow such enormous ice chunks reveals the incredible power hidden within severe thunderstorms. Standing beneath a storm that can produce such projectiles is standing beneath one of nature's most dangerous bombardments. Ice storms can coat entire cities in a dangerous glassy shell. When rain falls through a shallow layer of freezing air near the surface, it remains liquid until it strikes anything cold enough to freeze it on contact, creating what meteorologists call freezing rain. The accumulating ice quickly glazes trees, power lines, roads, and buildings in a clear, heavy coating that can grow centimeters thick. Branches snap under the weight, power lines collapse, and roads become skating rinks too slippery for any vehicle. One of the most destructive ice storms on record struck North America in 1998, leaving millions without power for weeks and causing dozens of deaths. The transformation of a familiar landscape into a crystalline wonderland is beautiful, but deadly, as every surface becomes treacherous. Emergency services in ice-affected regions often cannot respond normally because their vehicles cannot travel safely. The quiet that follows an ice storm is punctuated by the cracking and crashing of branches giving way under their glassy burden. Tornado winds can fling straw through solid wood. The winds inside a violent tornado can exceed 300 kilometers per hour, accelerating objects to velocities that transform everyday items into deadly projectiles. At these speeds, even lightweight objects like pieces of straw or grass can penetrate solid surfaces, driven through wooden boards and embedded in tree trunks. This phenomenon is not magic but simple physics. Extremely high velocity gives even small, light objects tremendous kinetic energy. Damage surveys after tornadoes have documented countless examples of improbable penetrations, from playing cards embedded in walls to 2x4s driven through concrete. The debris carried by a tornado becomes a swirling cloud of missiles, making the wind zone around the funnel itself one of the most dangerous environments on Earth. Taking shelter in a reinforced structure during a tornado is essential, because no amount of running can outpace these winds. The power of tornado winds to transform ordinary objects into weapons demonstrates forces almost impossible to comprehend. The fastest tornado winds rival the speed of a passenger jet. The most violent tornadoes, rated EF5 on the enhanced Fujita scale, can produce wind speeds exceeding 400 km per hour, approaching the cruising speed of a commercial jet aircraft. These extreme winds are measured using Doppler radar, and by analyzing the damage patterns left behind, as no ground-based instrument can survive inside such a vortex. Fortunately, EF5 tornadoes are relatively rare, accounting for less than 1% of all tornadoes that touch down. However, they are responsible for a disproportionate share of tornado deaths because the destruction they cause is nearly total. Buildings in the path of an EF5 tornado can be swept clean off their foundations, leaving only bare concrete or earth. The combination of wind speed, debris, and the vacuum created by the intense low pressure at the tornado's core makes these storms among the most destructive forces in nature. Surviving such an encounter requires reinforced underground shelter and considerable good fortune. Hurricanes release more energy than every power plant on Earth combined. A fully developed hurricane releases energy at a staggering rate, with estimates suggesting that a single day's energy output equals roughly 500,000 atomic bombs. This energy comes from the latent heat released when water vapor condenses into rain, a process that powers the storm's circulation and drives its winds. If humanity could somehow harness the energy of a single hurricane, it would satisfy global electricity demand for months. The storm's energy is distributed across thousands of square kilometers, with the most intense winds concentrated in the eye wall surrounding the calm center. Hurricanes can only form over warm ocean water, which provides the fuel they need. Crossing onto land cuts off their energy supply and causes them to weaken. Despite their immense power, hurricanes are also vulnerable, with wind shear and cool water capable of disrupting their delicate structure. The awesome energy of a hurricane reminds us that the atmosphere operates on scales far beyond anything human technology can match. The calmest part of a hurricane is at its violent center. The eye of a hurricane is a region of strange tranquility at the heart of the storm, where winds drop to near calm, and the sky may even turn blue. This calm center is typically 20 to 60 kilometers across, surrounded by the eye wall, where the storm's most violent winds and heaviest rains swirl. As the eye passes over a location, survivors describe an eerie quiet, sometimes lasting half an hour or more, before the opposite side of the eye wall arrives with renewed fury. The eye forms because the hurricane's rotation creates centrifugal forces that push the heaviest rain and strongest winds outward, leaving the center relatively clear. Looking up from inside the eye, observers can sometimes see blue sky, framed by towering walls of cloud rising to the tropopause. Birds and even insects are sometimes trapped in the eye, carried along for the storm's journey. The contrast between the peaceful eye and the violence just tens of kilometers away makes hurricanes among the most surreal experiences in nature. Supercell storms can grow larger than entire countries. The most powerful thunderstorms on Earth, called supercells, are rotating monsters that can span over 100 kilometers and persist for many hours. A supercell's rotating updraft, known as a mesocyclone, can punch through the tropopause, sending ice crystals into the lower stratosphere and creating anvil tops visible from hundreds of kilometers away. These storms are the primary producers of large hail, damaging winds, and violent tornadoes, making them among the most dangerous weather phenomena. The rotation that defines a supercell forms when environmental wind shear tilts a horizontal tube of spinning air into the vertical, becoming embedded in the storm's updraft. Once established, a supercell can maintain itself for hours by continually ingesting warm, moist air, while expelling rain on its flanks rather than through its core. Storm chasers travel thousands of kilometers each spring to witness these atmospheric behemoths, which combine beauty and danger in equal measure. A single supercell produces more rain, hail, and wind energy than most ordinary thunderstorms produce in an entire day. Some thunderstorms can persist for more than 12 hours. While ordinary thunderstorms typically last only an hour or two before collapsing, certain atmospheric configurations allow storms to become self-sustaining systems that can persist throughout an entire day or even longer. These long-lived storms include mesoscale convective systems, which are organized complexes of thunderstorms that regenerate continuously as they move across the landscape. The key to longevity is a steady supply of warm, moist air feeding into the storm, while the storm itself remains organized rather than dissipating into incoherent rainfall. Some Derecho events, straight-line windstorms that cross entire countries, have maintained damaging winds for 12 hours or more across distances exceeding 1,000 kilometers. Tropical storms and hurricanes can persist for weeks if conditions remain favorable, though their character changes as they move. The atmosphere's ability to sustain such long-lived storms demonstrates how weather systems can take on a life of their own. Watching a storm that has been raging since morning still producing lightning at midnight reveals the atmosphere's capacity for sustained violence. The hottest temperature ever recorded could melt car tires. In July 1913, a thermometer in Death Valley, California, registered 56.7 degrees Celsius, a temperature so extreme that it remains the highest reliably recorded on Earth. At such temperatures, the rubber in car tires can soften dangerously, asphalt roads can become sticky and deformed, and aircraft can struggle to generate lift because the hot, thin air provides less resistance for their wings. The human body cannot survive extended exposure to such heat without constant cooling and hydration, as the air temperature exceeds what our sweat can compensate for. The record stands as a reminder of the extremes our planet can produce, even without volcanic activity or industrial sources. Scientists debate whether this record and others from the era were measured accurately, but there is no doubt that Death Valley regularly approaches 50 degrees in summer. Working or traveling in such environments requires careful planning and carries serious risks. The hottest places on Earth push the limits of habitability, challenging life itself. The coldest air on Earth can freeze metal in seconds. The lowest temperature ever recorded at ground level was -89.2 degrees Celsius, measured at the Vostok Research Station in Antarctica. At such temperatures, exposed skin freezes almost instantly, and even metal becomes dangerously brittle and difficult to handle. Researchers at Antarctic stations during the winter months must take extraordinary precautions, as a few minutes of exposure can be fatal. The extreme cold occurs because Antarctica's high elevation, dry air, and position during the polar night allow heat to radiate away into space with nothing to replace it. Breathing air this cold damages the lungs unless it is warmed first, and vehicles require special lubricants because ordinary oils freeze solid. The coldest places on Earth are effectively as hostile to unprotected humans as the surface of Mars. Understanding how life survives in these extremes helps scientists plan for exploration of truly alien environments. Heat waves kill more people than any other type of extreme weather. Despite the dramatic images of hurricanes and tornadoes, heat waves consistently cause more fatalities than any other weather phenomenon in most developed countries. The danger of heat is often underestimated because it kills quietly, through dehydration, heat stroke, and cardiovascular stress, rather than through visible destruction. The elderly, the very young, and those with chronic health conditions are most vulnerable, especially in urban areas, where concrete and asphalt absorb and radiate heat even through the night. The deadliest heat wave in recent history struck Europe in 2003, claiming tens of thousands of lives across the continent. Unlike storms which pass quickly, heat waves can persist for days or weeks, allowing their toll to accumulate invisibly. Climate change is making heat waves more frequent, more intense, and longer lasting, increasing the risk to vulnerable populations. Learning to take heat seriously, seeking cool shelter, and staying hydrated can save lives that would otherwise be lost in silence. The polar vortex can push Arctic cold into the south. The polar vortex is a persistent large-scale cyclone that sits over the polar regions, usually keeping the coldest air locked in the high latitudes. However, when the vortex weakens or becomes wavy, lobes of frigid Arctic air can spill southward, bringing extreme cold to regions normally protected from such temperatures. These polar vortex disruptions can cause temperatures to plunge 30 or 40 degrees below normal, overwhelming infrastructure not designed for such cold. Pipes burst, heating systems struggle, and people unaccustomed to extreme cold face serious risks. The vortex's behavior is influenced by conditions across the entire hemisphere, making outbreaks somewhat predictable, but never entirely preventable. Scientists are studying whether climate change is making polar vortex disruptions more common, though the relationship is complex. When the vortex breaks, regions that rarely see sub-zero temperatures can suddenly experience conditions that would be normal near the Arctic Circle. cities create heat islands warmer than the surrounding countryside. Urban areas are typically several degrees warmer than the rural land surrounding them, a phenomenon called the urban heat island effect. This warming occurs because buildings, roads, and other hard surfaces absorb heat during the day and radiate it at night, while vehicles and air conditioners add additional warmth. The lack of vegetation means less cooling from evapotranspiration, and tall buildings can trap heat and reduce airflow. On calm, clear nights, the temperature difference between a city center and surrounding farms can exceed 10 degrees Celsius. Urban heat islands intensify the dangers of heat waves, especially for low-income residents who may lack air conditioning. Planners can reduce the effect by increasing tree cover, using reflective materials on roofs and roads, and designing buildings to promote airflow. The simple act of adding greenery to a city can make the difference between comfortable summer nights and sweltering, sleepless ones. The wettest place on Earth is soaked by walls of rain. Mawsyn Ram and Cherrapunji in northeastern India receive more annual rainfall than almost anywhere else on Earth, with some years recording over 12,000 millimeters of precipitation. During the monsoon season, rain falls so heavily and continuously that it seems less like weather and more like standing beneath a waterfall. The moisture comes from the Bay of Bengal, where warm ocean air picks up immense quantities of water vapor before being forced upward by the Khasi Hills, releasing its burden as it rises and cools. Local residents have adapted their lives around the rain, using living root bridges to cross rivers that swell to impassable torrents during the monsoon. The rainfall here can turn gentle streams into raging rivers within hours, reshaping the landscape with each season. Yet even in this wettest place, there is a dry season when the rain stops and the land briefly recovers. The extremes of Mawsyn Ram reveal how profoundly geography can concentrate moisture in a single location. The Atacama Desert can go decades without a single drop of rain. The Atacama Desert in northern Chile is so dry that some weather stations have never recorded any rainfall at all, even after decades of continuous measurement. This hyper-arid region receives less than 1 millimeter of rain per year on average, making it drier than the Sahara and comparable to conditions on Mars. The extreme dryness results from a combination of factors: a cold ocean current that suppresses evaporation offshore, mountains that block moist air from the east, and a persistent high-pressure system that prevents clouds from forming. Some parts of the Atacama are so barren that NASA has tested Mars rovers there, using the landscape as a stand-in for the red planet. Yet life persists even here, with specialized cacti and lichens extracting moisture from coastal fog. The Atacama reminds us that Earth contains regions as seemingly lifeless as any alien world. Yet even a rare rainfall event can trigger explosions of wildflower blooms that transform the desert briefly into a sea of color. Some droughts have lasted for hundreds of years. Paleoclimate research has revealed that certain regions have experienced mega-droughts lasting decades or even centuries, periods of dryness far beyond anything in recorded history. Evidence from tree rings, lake sediments, and cave formations shows that the American Southwest, for example, experienced multi-decade droughts during the medieval period that likely contributed to the collapse of ancient Pueblo civilizations. Similar prolonged droughts have been reconstructed for Africa, Australia, and Asia, sometimes coinciding with the fall of empires and mass migrations. These ancient droughts were driven by natural climate variability, including oscillations in ocean temperatures that shifted rainfall patterns for generations. Understanding that such extreme events have occurred naturally helps scientists assess the risks that future climate change might intensify or extend drought conditions. The possibility of a modern mega-drought poses serious challenges for water management and agriculture. History written in tree rings warns us that the droughts we know may be far milder than those our distant ancestors endured. Monsoons can transform entire landscapes in a single season. The monsoon is a seasonal reversal of wind direction that brings life-giving rain to billions of people across South Asia, Africa, and parts of the Americas. In India, the summer monsoon arrives each year like a relief after months of withering heat, transforming brown, dusty landscapes into lush green within weeks. The rains fill reservoirs, recharge groundwater, and nourish the crops that feed the world's second most populous nation. Yet the monsoon's gift is also a threat. Too much rain causes devastating floods, while too little triggers drought and famine. The timing and intensity of the monsoon have shaped cultures, economies, and religions across the monsoon belt for thousands of years. Scientists monitor monsoon patterns closely because delays or failures can affect food security for billions. The annual drama of the monsoon's arrival remains one of Earth's most anticipated and consequential weather events. Dew can collect enough water to sustain life in deserts. In arid regions where rain is rare, the daily condensation of dew can provide crucial moisture for plants, insects, and even human survival. Dew forms when objects on the ground cool overnight by radiating heat into the clear sky, causing moisture in the air to condense on their surfaces. Desert beetles have evolved specialized body surfaces that capture fog and dew, channeling the droplets toward their mouths. Ancient farmers in dry regions built low stone walls to collect dew, harvesting enough water to support small plots in otherwise impossible conditions. In the fog deserts of coastal Chile and Namibia, specialized nets can collect liters of water each night from moisture in the air. Dew is a reminder that even in the driest places, the atmosphere holds water that can be coaxed onto surfaces by the cold of night. This invisible precipitation sustains ecosystems that receive almost no rain at all. Flash floods can move boulders the size of cars. When heavy rain falls faster than the ground can absorb it, water rushes across the surface, gathering into torrents that grow more powerful with each passing moment. Flash floods can rise from ankle-deep to roof-high in minutes, carrying debris, vehicles, and even buildings in their path. The force of moving water is extraordinary. A stream flowing at just a few meters per second can knock a person off their feet and roll boulders weighing tons. Desert canyons are particularly dangerous because rain miles away can send walls of water through dry channels with no warning to anyone downstream. Flash floods cause more weather-related deaths than tornadoes in many regions because people underestimate the power of water. Never attempt to cross a flooded road, as even shallow moving water can sweep away a car. The fury of a flash flood demonstrates that water, the gentlest of elements, becomes deadly when concentrated and moving. Dust devils can rise taller than skyscrapers. Dust devils are rotating columns of air that form over hot surfaces when rising warm air begins to spin, pulling dust and debris high into the sky. While most are small and harmless, large dust devils can reach heights of 1,000 meters, rivaling the tallest buildings on Earth. Unlike tornadoes, which descend from thunderclouds, dust devils form from the ground up on clear, sunny days when the surface heating is intense. They typically last only a few minutes and travel short distances before dissipating, but they can be surprisingly powerful. Strong dust devils have been known to overturn small structures and throw debris considerable distances. On Mars, dust devils tower kilometers into the thin atmosphere and sweep across the planet's deserts, leaving dark tracks visible from orbit. These spinning columns of air are playful reminders of the invisible forces that shape the atmosphere. Waterspouts can spin across the ocean like watery tornadoes. Waterspouts are rotating columns of air that extend from clouds to the surface of water, appearing as graceful funnels dancing across bays and lakes. While they resemble tornadoes and can be dangerous to boats, most waterspouts are weaker than their overland cousins. Fair-weather waterspouts form on calm, humid days when convection creates rotating thermals that tighten into visible vortices. Tornadic waterspouts, which form from severe thunderstorms, are far more dangerous and can move onshore to cause significant damage. The spray of water around a waterspout's base is not the funnel itself, but droplets being whipped up from the surface by the spinning winds. Sailors have feared waterspouts for centuries, associating them with sea monsters and divine wrath. Watching a waterspout from a safe distance reveals the elegant physics of rotation, made visible by water and mist. Microbursts can slam aircraft out of the sky. A microburst is a powerful downdraft of air that descends rapidly from a thunderstorm and spreads out violently when it hits the ground. When an aircraft flies through a microburst during takeoff or landing, it can experience sudden, catastrophic changes in wind speed and direction that overwhelm even skilled pilots. The danger was not fully understood until several fatal crashes in the 1970s and 80s prompted intensive study. Today, airports use Doppler radar specifically designed to detect microbursts and warn pilots before they encounter the hazard. A microburst can produce winds exceeding 150 km per hour, focused in an area just a few kilometers across, making them intense but localized hazards. The damage patterns they leave on the ground resemble those of tornadoes, but spread outward in all directions like a starburst. Understanding microbursts has saved countless lives by allowing pilots and controllers to avoid invisible killers lurking beneath seemingly ordinary storms. Skyscrapers can bend and accelerate local winds. Tall buildings interact with the wind in complex ways, blocking airflow, channeling it between structures, and accelerating it around corners. At street level in dense cities, pedestrians can experience sudden gusts, strong enough to knock them off balance, created by winds deflected and concentrated by architecture. This effect, sometimes called the Venturi effect or urban canyon effect, was not well understood when early skyscrapers were built, leading to unexpectedly windy streets. Modern architects use wind tunnel testing and computer simulations to predict and mitigate these effects when designing new towers. Some buildings have been modified after construction to reduce problematic wind acceleration at ground level. The swaying of very tall buildings in high winds can also create discomfort or even motion sickness for occupants of upper floors. Cities have become laboratories for understanding how rigid structures interact with the fluid atmosphere flowing past them. Jet contrails can change local cloud cover. The white trails left by high-flying aircraft are condensation trails, or contrails, formed when hot jet exhaust mixes with cold, humid air and water vapor freezes into ice crystals. Under certain atmospheric conditions, these contrails persist and spread, eventually becoming indistinguishable from natural cirrus clouds. Because cirrus clouds have a net warming effect on the climate, the additional cloud cover created by aviation may contribute measurably to global warming. During the days after the September 2001 attacks, when commercial aviation over the United States was grounded, scientists observed changes in the daily temperature range that suggested the absence of contrails had a detectable effect. The aviation industry is studying technologies to reduce contrail formation, including routing aircraft around humid regions where contrails persist longest. Every white line drawn across the sky by a passing jet is not just a trail, but a potential permanent addition to the planet's cloud cover. The unintended weather modification caused by aviation is a reminder that even routine activities can alter the atmosphere. Ocean currents act like giant rivers of heat beneath the surface. The world's oceans contain a vast circulation system that moves warm water from the tropics toward the poles and cold water back toward the equator, distributing heat around the planet. This global conveyor belt, also called thermohaline circulation, is driven by differences in water temperature and salinity that cause water to rise or sink. The system moves more water than all the world's rivers combined, yet it flows so slowly that a complete circuit takes centuries. Changes in this circulation have been linked to major climate shifts in Earth's history, including ice ages and rapid warming events. If the conveyor belt were to slow or stop, the consequences for global climate would be profound and difficult to predict. The ocean's ability to store and transport heat makes it the dominant influence on long-term weather patterns across continents. Most of Earth's heat storage occurs in the ocean, making its currents crucial regulators of the planet's temperature. The Gulf Stream helps keep Europe warm in winter. The Gulf Stream is a powerful warm current that flows from the Gulf of Mexico up the eastern coast of North America before crossing the Atlantic toward Europe. This river of warm water, moving more water than all the world's rivers combined, releases heat into the atmosphere as it travels, keeping northern Europe significantly warmer than other regions at similar latitudes. London and Paris are at roughly the same latitude as parts of Canada that experience brutal winters, yet they enjoy far milder weather thanks to the Gulf Stream's warmth. The current also influences marine ecosystems, carrying larvae and nutrients across the Atlantic, and supporting fishing industries on both sides. Scientists worry that melting ice and changing rainfall patterns in the Arctic could disrupt the Gulf Stream by altering the salinity balance that drives the current. Any significant weakening of the Gulf Stream would have dramatic effects on European weather, potentially causing winters to become much colder. The warmth of European winters depends on processes occurring thousands of kilometers away in the tropical Atlantic. El Niño can shift weather patterns across the entire planet. El Niño is a periodic warming of the central and eastern tropical Pacific Ocean that triggers a cascade of weather changes around the world. When El Niño conditions develop, which occurs every few years, the shift in ocean temperatures alters atmospheric circulation patterns in ways that affect rainfall and temperature on every continent. Regions that normally receive abundant rain may experience drought, while typically dry areas may flood. The impacts include failed monsoons in India, drought in Australia and Indonesia, and increased rainfall in the Americas. El Niño events have been linked to famines, disease outbreaks, and economic disruptions affecting billions of people. Scientists can now predict El Niño development months in advance, giving governments time to prepare for its impacts. The discovery that a patch of warm water in the Pacific could influence weather globally revealed how interconnected the atmosphere and ocean truly are. La Niña brings the opposite effect in cooling winds. La Niña is El Niño's counterpart, characterized by unusually cold surface temperatures in the central and eastern tropical Pacific. While El Niño tends to suppress hurricane activity in the Atlantic, La Niña often enhances it by reducing wind shear that would otherwise tear developing storms apart. La Niña conditions typically bring wetter weather to Australia and Southeast Asia, while contributing to drought in the American Southwest and parts of South America. The back-and-forth oscillation between El Niño and La Niña, with neutral conditions in between, creates a rhythm in global weather patterns that climatologists have learned to track and forecast. These oscillations have been occurring for thousands of years, as recorded in coral growth patterns and other natural archives. Understanding the El Niño-La Niña cycle has improved seasonal forecasting worldwide, helping farmers, emergency managers, and governments prepare for what the ocean will bring. The tropical Pacific truly is the thermostat of global weather. Melting sea ice changes wind and ocean patterns worldwide. As Arctic sea ice melts to record lows, the resulting changes in ocean and atmospheric circulation are having effects far beyond the polar regions. Open water absorbs more heat than ice, creating a feedback loop that accelerates warming in the Arctic at rates faster than anywhere else on Earth. The warming Arctic may be altering the jet stream, the high-altitude river of air that steers weather systems across the mid-latitudes. Some scientists believe that a weakened wavier jet stream is responsible for increased weather extremes, including persistent heat waves and cold snaps. Melting sea ice also affects ocean circulation by adding fresh water that can disrupt the density-driven currents of the thermohaline circulation. The loss of Arctic ice is not just a local phenomenon but a change that ripples through the entire climate system. What happens at the top of the world increasingly affects weather everywhere. Hurricanes can churn the sea until it glows with plankton light. The intense mixing caused by a hurricane's passage stirs the ocean to depths of 100 meters or more, bringing cold, nutrient-rich water to the surface and triggering blooms of microscopic life. In tropical waters where bioluminescent plankton are common, this churning can create spectacular displays of natural light as the organisms flash in response to disturbance. Satellite images taken after hurricanes have shown dramatic changes in ocean color as chlorophyll concentrations spike from the sudden fertilization. The cooling of surface waters by hurricane mixing can temporarily suppress the development of subsequent storms by robbing them of the warm water they need to grow. Fish and other marine life may benefit from the nutrient pulse, even as the storm itself causes widespread destruction on land. The after effects of a hurricane extend far beneath the waves, reshaping marine ecosystems for weeks or months. The ocean remembers the passage of each storm in ways invisible from the shore. A volcanic eruption can change weather worldwide. When a major volcanic eruption injects ash and sulfur dioxide high into the stratosphere, the particles spread around the globe and reflect incoming sunlight back into space, cooling the planet. The eruption of Mount Pinatubo in the Philippines in 1991 lowered global average temperatures by about ½ degree Celsius for the following year. Historical eruptions have had even more dramatic effects. The 1815 eruption of Mount Tambora caused the following year of 1816 to be remembered as the year without a summer, with crop failures and famine across Europe and North America. Volcanic particles can remain suspended in the stratosphere for years because there is no rain at that altitude to wash them out. The temporary cooling from eruptions can mask the effects of global warming briefly, but it also reminds us how sensitive climate is to changes in atmospheric composition. Scientists study volcanic climate effects, both to understand past events and to evaluate proposals for deliberate atmospheric cooling to combat climate change. Volcanoes are powerful reminders that Earth's climate can change rapidly when enough material enters the upper atmosphere. Forest fires can create their own lightning storms. The intense heat of large wildfires can generate pyrocumulonimbus clouds, towering thunderclouds born from the smoke and heat rising from burning forests. These fire-generated storms produce lightning that can ignite new fires kilometers ahead of the main blaze, causing the fire to spread in unpredictable ways. The convection above a large fire can be as powerful as that in any thunderstorm, with updrafts capable of lifting burning debris high into the atmosphere. Pyrocumulonimbus clouds can inject smoke into the stratosphere, where it spreads globally and affects air quality thousands of kilometers from the original fire. The lightning these clouds produce sometimes starts so many new fires that firefighters cannot keep up, leading to fire complexes that burn for weeks or months. Climate change is making conditions for these extreme fire events more common, as forests dry out and heat waves intensify. Watching a wildfire create its own weather is witnessing a feedback loop where fire becomes both cause and consequence. Smoke from fires can seed strange new clouds. The particles in wildfire smoke can act as nuclei, around which water droplets and ice crystals form, creating clouds that would not otherwise exist. These smoke-seeded clouds behave differently from ordinary clouds, often producing smaller droplets that are less likely to fall as rain. The smoke particles absorb sunlight and warm the surrounding air, which can change local circulation patterns and suppress rainfall in some cases. During the extreme Australian bushfire season of recent years, smoke affected cloud formation and weather patterns across the Pacific Ocean. The interaction between smoke and clouds is one of the most uncertain factors in climate science, because the effects vary depending on smoke composition, altitude, and ambient conditions. Some scientists are studying whether deliberate smoke injection could be used to reflect sunlight and cool the planet, though the risks and side effects remain poorly understood. Every wildfire is an uncontrolled experiment in atmospheric chemistry. Dust from the Sahara travels all the way to the Amazon. Each year, millions of tons of dust are lifted from the Sahara Desert by strong winds and carried westward across the Atlantic Ocean to the Americas. This transatlantic journey takes about a week, with dust settling into the ocean and onto land across a vast area. Remarkably, the phosphorus in Saharan dust is a critical fertilizer for the Amazon rainforest, whose soils are otherwise depleted of this essential nutrient. The connection between the world's largest desert and its largest rainforest demonstrates how intimately linked Earth's ecosystems truly are. Dust from Africa also affects Caribbean weather, suppressing hurricane development during the peak season by drying out the air and increasing wind shear. Researchers track Saharan dust plumes using satellites, watching as continents exchange material across thousands of kilometers of ocean. The fertility of the Amazon depends in part on the sterility of the Sahara, a paradox that reveals the planet's hidden connections. Volcanoes can unleash storms of electric fire. Volcanic eruptions can produce spectacular displays of lightning within the ash clouds they generate, a phenomenon called volcanic lightning or dirty thunderstorms. The mechanism is similar to ordinary lightning but involves the collision of ash particles, ice, and rock fragments, rather than raindrops and ice crystals. Small eruptions may produce only brief flashes, but major eruptions can generate continuous lightning that illuminates the ash cloud like a scene from mythology. The electrical discharge helps to clump ash particles together, causing them to fall more quickly and reducing the long-range spread of the ash cloud. Volcanic lightning poses additional hazards for aircraft, which must already avoid ash clouds that can damage jet engines. Photographers have captured extraordinary images of volcanic lightning, showing purple and white arcs dancing among billowing clouds of ash and steam. These storms of fire and electricity are among the most dramatic displays of natural power on Earth. Glaciers move like rivers of ice, reshaping continents. Glaciers are vast rivers of ice that flow slowly downhill under their own immense weight, carving valleys and shaping landscapes over thousands of years. The movement is imperceptibly slow to the human eye, typically measured in centimeters or meters per day, yet over geological time glaciers have gouged out fjords, deposited hills of debris, and sculpted some of the world's most dramatic scenery. At the base of a glacier, the immense pressure causes ice to behave almost like plastic, deforming and flowing around obstacles. Glaciers also slide over thin layers of meltwater that lubricate the contact between ice and bedrock. The largest glaciers, found in Antarctica and Greenland, contain enough ice to raise global sea levels by many meters if they were to melt completely. Smaller mountain glaciers around the world are retreating rapidly as temperatures rise, with consequences for water supplies that depend on glacial meltwater. Watching a glacier carve icebergs into the sea is witnessing the slow march of ice accelerating into sudden thunderous collapse. Avalanches can move faster than cars on a highway. A large avalanche can accelerate from stillness to over 300 kilometers per hour within seconds, racing down mountainsides faster than most vehicles can travel. The air pushed ahead of an avalanche forms a powerful blast wave that can flatten trees and buildings even before the snow arrives. Avalanches occur when the bond between snow layers fails, allowing a slab of snow to break free and cascade downhill, gathering mass and speed as it goes. The danger is highest after heavy snowfall onto existing layers, especially on slopes between 30 and 45 degrees. Survival rates drop dramatically with burial depth and time, as air pockets become crucial for those trapped beneath the snow. Mountain communities have developed extensive avalanche control programs, including deliberate triggering of small slides before they can grow dangerous. The power of moving snow is easily underestimated, yet an avalanche carries energy comparable to small explosions. Icebergs hide nearly 90% of their mass underwater. The famous image of an iceberg floating with only its tip visible is a reminder that what we see is only a fraction of the whole. Because ice is slightly less dense than seawater, roughly 90% of an iceberg's volume floats below the surface, invisible to observers above. This hidden bulk makes icebergs dangerous to ships, as the underwater portion can extend far beyond the visible edges. The sinking of the Titanic in 1912 brought global attention to icebergs as navigation hazards, leading to the creation of the International Ice Patrol. Icebergs carve from glaciers and ice shelves, carrying frozen water that fell as snow centuries or millennia ago. As they drift into warmer waters, icebergs gradually melt, releasing their ancient ice back into the ocean. The blue color of old glacial ice comes from the compression that squeezes out air bubbles, leaving pure ice that absorbs red light and reflects blue. Permafrost locks away ancient life forms for millennia. Permafrost is ground that remains frozen year-round, preserving everything within it in a deep freeze that can last for thousands of years. In Siberia and other Arctic regions, the thawing of permafrost has revealed remarkably preserved remains of woolly mammoths, ancient horses, and other Ice Age creatures. Some of these specimens still have soft tissue, fur, and even stomach contents intact, providing extraordinary opportunities for scientific study. Permafrost also locks away vast quantities of organic carbon that accumulated over millennia and did not fully decompose before freezing. As climate change thaws permafrost, this ancient carbon is released as carbon dioxide and methane, potentially accelerating warming in a dangerous feedback loop. Scientists are racing to understand how much greenhouse gas might escape and how quickly the thaw might proceed. The frozen archives of the Arctic hold both treasures of the past and threats to the future. Glacial meltwater can create rivers that roar under the ice. Beneath large glaciers, meltwater can collect into powerful rivers that flow through tunnels carved into the ice and bedrock below. These subglacial rivers can be heard rumbling beneath hikers walking on the ice surface, a reminder that glaciers are not static objects but dynamic systems with their own hidden hydrology. When meltwater accumulates in lakes beneath the ice and suddenly drains, the result is a glacial outburst flood, or Jökulhlaup, that can devastate downstream valleys. Iceland has experienced numerous such floods, some releasing more water in hours than flows over Niagara Falls in a week. The lubricating effect of meltwater at the base of a glacier can also cause the ice to surge forward suddenly, advancing kilometers in a single season. Scientists study subglacial rivers using radar and seismometers to understand how water and ice interact. The hidden hydrology of glaciers is a world of rushing water frozen in darkness beneath vast sheets of ancient ice. Weather drives the migration of animals across continents. The seasonal changes in weather are the primary triggers for some of the most spectacular migrations on Earth, as animals travel thousands of kilometers to follow food, warmth, and breeding conditions. Arctic terns make the longest migration of any animal, flying from Arctic to Antarctic and back each year, chasing endless summer along the way. Wildebeest cross the Serengeti in vast herds, following the rains that bring fresh grass, while salmon navigate rivers by sensing magnetic fields and the chemistry of their home streams. The timing of these migrations has evolved over millions of years to match the rhythm of the seasons, but climate change is now disrupting these ancient patterns. Birds may arrive at breeding grounds before the insects they depend on have hatched, or find that the landscapes they expect have shifted northward. The delicate synchronization between weather and migration is being tested by a rapidly changing planet. Every migrating creature is a traveler following weather patterns written into its genes. Monarch butterflies follow weather patterns for thousands of miles. Each autumn, millions of monarch butterflies travel up to 5,000 kilometers from Canada and the United States to their wintering grounds in the mountains of central Mexico. This epic journey spans multiple generations, with no single butterfly making the complete round trip. The navigating butterflies use a sun compass and possibly the Earth's magnetic field to maintain their southwesterly heading. Weather plays a crucial role in the migration, with favorable winds and mild temperatures allowing faster travel and higher survival rates. The butterflies cluster together in vast orange clouds on specific mountain slopes, waiting out the winter until warmth returns, and they begin the northward journey anew. Climate change threatens both the butterflies and the forests they depend on, making the future of this migration uncertain. Watching monarchs stream southward on an autumn day is witnessing one of nature's most delicate long-distance journeys. Birds ride invisible rivers of rising warm air called thermals. Soaring birds like eagles, vultures, and storks exploit thermals to gain altitude without flapping their wings, saving the energy they need for long-distance flight. Thermals are columns of rising warm air that form when the sun heats the ground unevenly, creating patches of air that become buoyant and rise. Birds circle within these invisible elevators, spiraling upward until they reach the thermal's top, then gliding forward to the next rising column. The skill of reading thermals allows birds to travel vast distances while barely moving their wings. Migration highways across the globe follow routes where thermals are most reliable, funneling millions of birds through narrow corridors. Human glider pilots have learned to exploit the same thermals that birds have used for millions of years. The skies are full of invisible pathways that only those who can feel the rising air truly know. Locust swarms are guided by rainfall patterns. The desert locust can transform from a solitary insect into a swarming plague when the right combination of rain and vegetation triggers a population explosion. After periods of drought followed by good rains, locusts multiply rapidly and begin to aggregate, changing color and behavior as they transition into their gregarious phase. Swarms can contain billions of individuals covering hundreds of square kilometers, consuming every scrap of vegetation in their path. Wind patterns guide the swarms across continents, with Africa and the Middle East particularly vulnerable to locust invasions that threaten food security for millions of people. Satellite monitoring of rainfall and vegetation allows early warning systems to predict where swarms might form, enabling control efforts before populations explode. The connection between weather and locusts has been known since ancient times, with infestations recorded in texts going back thousands of years. These swarms are living reminders that weather shapes not just landscapes but the populations of the creatures that depend on them. Animals can often sense storms before humans do. Many animals exhibit unusual behavior before storms arrive, leading to folk beliefs about their ability to predict the weather. The scientific explanation is that animals are sensitive to changes in barometric pressure, humidity, and other cues that often precede weather changes. Insects may fly lower when pressure drops because the denser air makes it harder to gain altitude, while birds roost earlier before approaching storms. Cows are said to lie down when rain approaches, possibly to preserve a dry spot or in response to joint discomfort from pressure changes. Some animals hear the low-frequency sounds of distant thunder long before humans can detect any sign of an approaching storm. While not infallible predictors, the behavior of animals integrates environmental signals that our senses often miss. Paying attention to the creatures around us can provide subtle warnings of weather changes on the horizon. Coral reefs bleach when seas grow too hot. Coral reefs depend on tiny algae called zooxanthellae that live within their tissues, providing them with energy through photosynthesis in exchange for shelter. When ocean temperatures rise even a few degrees above normal, the stress causes corals to expel their algae, turning the reef ghostly white in a process called bleaching. Bleached corals are not immediately dead but are severely weakened and may die if conditions do not improve within weeks. Mass bleaching events have become increasingly common as ocean temperatures rise, devastating reefs across the Great Barrier Reef, the Caribbean, and tropical oceans worldwide. Reefs that took centuries to grow can be killed in a single summer of extreme heat. Because coral reefs harbor roughly a quarter of all marine species, their loss has profound consequences for ocean biodiversity and the human communities that depend on reef ecosystems. The bleaching of corals is a visible symptom of a warming ocean that few other indicators can match. Weather helps carve mountains into valleys over millions of years. The slow work of weathering and erosion transforms solid rock into sand and soil, gradually wearing down even the highest mountains. Rain seeps into cracks and freezes, expanding and splitting rock apart in a process called frost wedging that is particularly effective in mountainous regions. Rivers carry the debris downstream, cutting valleys deeper with each passing century. Chemical weathering dissolves minerals from rock, weakening it and making it more susceptible to physical breakdown. The dramatic landscapes of the Grand Canyon, the Alps, and every other mountain range are the product of weather working patiently over millions of years. Without weather, the Earth's surface would be dominated by volcanic mountains and impact craters, as on airless worlds like the Moon. Every grain of sand on every beach began as part of a mountain, freed by the relentless action of water, wind, and ice. Wind can sculpt stone into arches and spires. In dry environments where wind carries abrasive sand, rock formations can be carved into delicate arches, towering hoodoos, and other fantastical shapes. The process is essentially sandblasting on a geological timescale, with harder layers of rock eroding more slowly than softer ones. The famous arches of Utah formed as wind and occasional rain eroded softer rock from beneath more resistant layers, leaving spans of stone suspended in air. Wind erosion is most effective close to the ground where sand-laden blasts are strongest, undercutting formations and creating mushroom-shaped pedestals. The sculpted stone of desert landscapes is a record of prevailing winds written in rock over tens of thousands of years. Visiting these landscapes is seeing what patient wind can accomplish when given enough time. The seemingly eternal stone is slowly yielding to the atmosphere's gentle but persistent touch. Frost crystals can grow into spiky forests of ice. Under certain conditions, when humidity is high and temperatures drop below freezing, intricate frost crystals can grow into elaborate structures on surfaces exposed to the air. These hoar frost formations occur most often on clear, cold nights, when objects radiate heat away faster than the surrounding air. The crystals form as water vapor deposits directly onto cold surfaces, without passing through a liquid phase, building layer upon layer of ice, in delicate branching patterns. Window frost, once common before double-glazed windows, created entire forests of ice on the inside of bedroom windows overnight. In mountain valleys prone to temperature inversions, frost can transform entire forests into glittering sculptures, bending branches with the weight of accumulated ice. The geometry of frost crystals reflects the hexagonal structure of ice at the molecular level, visible to the naked eye in the intricate patterns. Morning sunlight transforms these frozen gardens into dazzling displays before the warmth destroys them. The carbon cycle is deeply tied to weather patterns. Weather drives the movement of carbon through Earth's systems in ways that regulate climate over both short and long timescales. Rain dissolves carbon dioxide from the atmosphere and washes it over rocks, where chemical reactions lock the carbon into minerals that eventually wash into the ocean. This weathering process is a natural thermostat that has stabilized Earth's climate over geological time. Warmer temperatures accelerate weathering, drawing down carbon dioxide and cooling the planet, while cooler temperatures slow the process, allowing carbon dioxide to accumulate. The carbon cycle also operates through the living world, with forests absorbing carbon as they grow, and releasing it when they burn or decay. Human activities have disrupted this cycle by releasing ancient carbon from fossil fuels far faster than natural processes can absorb it. Understanding the carbon cycle is essential to understanding both past climate changes and the consequences of current human actions. Ancient ice holds tiny samples of prehistoric air. Deep in the ice sheets of Antarctica and Greenland, bubbles of air trapped when the snow first fell remain preserved for hundreds of thousands of years. By drilling ice cores and analyzing these bubbles, scientists can reconstruct the composition of Earth's atmosphere, going back nearly 1 million years. The record shows clear cycles of ice ages and warm periods, with carbon dioxide levels rising and falling in concert with temperature. Modern carbon dioxide concentrations are higher than at any point in this entire record, sounding an alarm about the unprecedented nature of current climate change. Ice cores also preserve volcanic ash, pollen, and other particles that reveal past events from volcanic eruptions to forest fires. The process of extracting and analyzing ice cores is painstaking, but the knowledge gained is invaluable for understanding how climate has changed and will continue to change. A cylinder of ice from 3 kilometers deep contains tiny glass capsules of air, breathed by woolly mammoths. A rainbow is actually a complete circle, but we see only half. When sunlight passes through raindrops and reflects back toward an observer, it is separated into its component colors and spread into a circular arc, centered on the point opposite the sun. From ground level, we see only the upper half of this circle, because the lower half is below the horizon. Observers from aircraft or high mountains can sometimes see the complete ring, though the sight is rare and unforgettable. The colors of a rainbow always appear in the same order, with red on the outside and violet on the inside, determined by the physics of refraction. Each color reaches your eye from different raindrops at different angles, meaning the rainbow you see is unique to your position. Step to one side, and an entirely different set of drops creates an entirely different rainbow. The rainbow you watch is a pattern created just for you by millions of raindrops falling in precisely the right relationship to your eyes. Double rainbows reveal the hidden paths of light. When conditions are right, a second, fainter rainbow appears outside the primary arc, with its colors reversed so that red appears on the inside. This secondary rainbow is caused by light reflecting twice inside raindrops before exiting, losing some intensity with each reflection. Between the two arcs is a noticeably darker band of sky called Alexander's dark band, where neither primary nor secondary rainbow light reaches the observer. Triple and higher order rainbows exist, but are so faint they are almost never seen with the naked eye. The physics that creates double rainbows has been understood since the 17th century, but the sight still evokes wonder. Each drop in a rainstorm contributes to both primary and secondary rainbows depending on the angle at which it encounters sunlight. Finding a double rainbow is finding confirmation that light follows intricate paths invisible until water reveals them. Sundogs sparkle like extra suns on icy days. Sundogs are bright spots that appear on either side of the sun when sunlight passes through ice crystals suspended in thin, high clouds. The crystals must be oriented horizontally to create the effect, acting as millions of tiny prisms that bend light at specific angles. Sundogs typically appear about 22 degrees from the sun, often accompanied by a faint halo circling the entire sky at the same distance. The name sundog, also called parhelion, may come from ancient beliefs that these bright companions were faithful attendants following the sun across the sky. Sundogs can display brilliant colors, especially red on the side nearest the sun, though they are often white in less favorable conditions. They are most common when the sun is low, during morning or afternoon, and when cirrus clouds are present. Watching for sundogs on cold, clear days can reward the observer with an unexpected display of atmospheric optics. Halos appear when sunlight bends through crystal clouds. When thin veils of cirrostratus clouds containing ice crystals cover the sky, a ring of light may appear around the sun or moon, known as a halo. The most common halo forms at 22 degrees from the light source, created by crystals that bend light by this angle, regardless of their orientation. Other, rarer halos form at different angles depending on the specific shapes and alignments of the crystals present. Halos have been interpreted as omens throughout history, though they simply reflect the presence of ice crystals at high altitude. The appearance of a halo often indicates that a warm front and precipitation may be approaching, as cirrostratus clouds frequently precede such weather systems. The ring may appear bright or faint, complete or fragmented, depending on the density and uniformity of the ice crystal layer. Looking up at a halo is peering through a screen of ice suspended kilometers above. Mirages can make whole lakes appear where none exist. The shimmering lakes that appear on hot roads and desert floors are mirages created by the bending of light through layers of air at different temperatures. On a hot day, the air just above the ground becomes much warmer than the air higher up, creating a gradient in which light from the sky curves downward and then back up to enter the observer's eye from below. The brain interprets this light as a reflection from water complete with the wavering appearance caused by turbulent air. Mirages are not hallucinations, but real optical phenomena that can be photographed. Inferior mirages, which appear below the object they copy, are common on roads, while superior mirages, in which the image appears above the actual object, occur over cold surfaces. Travelers throughout history have been deceived by mirages in deserts, pursuing phantom waters that recede forever beyond reach. Every mirage is a true image of the sky, merely displaced by light's willingness to follow the path of least resistance. Superior mirages can make ships appear to float in the sky. When a layer of cold air lies beneath warmer air, a condition called a temperature inversion, light from distant objects bends downward and reaches the eye from angles that make the objects appear higher than they are. Ships at sea can seem to float above the horizon, cities can appear lifted into the sky, and distant islands can become visible that would normally be hidden below the curve of the Earth. These superior mirages are more persistent and stable than the shimmering inferior mirages of hot surfaces, and can be photographed clearly. The Fata Morgana is a particularly complex superior mirage that creates towering, rapidly changing images of distant objects, sometimes resembling castles or cliffs. Sailors have long reported seeing ghost ships and phantom coastlines, phenomena that meteorology now explains through the optics of temperature inversions. Superior mirages remind us that seeing is not always believing, and the atmosphere can act as a lens distorting the world beyond recognition. The green flash appears for seconds at sunset. Just as the upper edge of the sun dips below the horizon, a brief flash of green or blue-green light sometimes appears, lasting only a second or two. This phenomenon occurs because the atmosphere acts as a prism, separating sunlight into its component colors, with blue and green light bending more than red. Most of the blue light is scattered away, but under the right conditions, the green light remains visible for a moment after the red has set. Seeing the green flash requires a clear view of a distant horizon, usually over the ocean, and very stable atmospheric conditions. Mirages can magnify the effect, making the flash more prominent and slightly longer lasting. The green flash has inspired legends and poetry, with some traditions holding that those who see it will never again be deceived in matters of love. Patient observers who watch many sunsets may be rewarded with this fleeting emerald gift. Moonbows glow faintly under the full moon. When the moon is bright and full and rain is falling on the opposite side of the sky, conditions are right for a moonbow, a rainbow produced by moonlight rather than sunlight. Moonbows are much fainter than solar rainbows because even the full moon is hundreds of thousands of times dimmer than the sun. To the naked eye, moonbows often appear white or pale gray because the light is too faint to strongly stimulate color receptors in our eyes. Long exposure photographs reveal the same spectrum of colors found in daytime rainbows, proving that the physics is identical. Waterfalls that produce mist at night are reliable spots for moonbow watching, with locations like Victoria Falls famous for these nocturnal arcs. Moonbows have inspired awe throughout history, appearing as ghostly signs in the night sky. Standing in moonlight with rain at your back, you may be rewarded with one of nature's most elusive optical treasures. The northern lights are a form of space weather. The aurora borealis and its southern counterpart, the aurora australis, are produced when charged particles from the sun collide with gases in Earth's atmosphere, causing them to glow. The sun constantly emits a stream of particles called the solar wind, but during solar storms this wind intensifies and carries far more energy toward Earth. The particles are funneled toward the poles by Earth's magnetic field, which is why auroras are most commonly seen at high latitudes. Different gases produce different colors, Oxygen glows green or red depending on altitude, while nitrogen produces blues and purples. Auroral displays can range from faint glows on the horizon to dramatic curtains of light that dance and ripple across the entire sky. The connection between auroras and solar activity was not understood until the 20th century, though the lights have been observed and marveled at for millennia. Watching the aurora is watching energy from the sun paint the upper atmosphere with light. Solar storms can disrupt Earth's weather systems. When the sun erupts with a coronal mass ejection, a vast bubble of magnetized plasma that travels through space at millions of kilometers per hour, the effects can be felt throughout the solar system. These storms compress Earth's magnetic field and inject energy into the upper atmosphere, sometimes enough to affect satellites, power grids, and communication systems. While the direct effects are electromagnetic rather than meteorological, research suggests that solar storms may influence weather indirectly by affecting atmospheric chemistry and circulation patterns. Large solar storms have knocked out power to entire regions and damaged satellites, with the potential for even more severe impacts if a truly massive storm were to strike. The largest solar storm on record, the Carrington event of 1859, caused telegraph systems to spark and produced auroras visible near the equator. Understanding space weather and its effects on Earth is an increasingly important field as our dependence on electronic infrastructure grows. The sun's temper can reach across space to touch our planet. Sprites flash red high above thunderclouds. High above powerful thunderstorms, enormous flashes of red light called sprites can extend upward for nearly 90 kilometers, briefly illuminating the upper atmosphere. Sprites were not photographed until 1989, though pilots had reported strange lights above storms for decades before scientists confirmed their existence. These electrical discharges are triggered by powerful positive cloud-to-ground lightning strokes, with the sprites appearing in the mesosphere tens of milliseconds after the triggering flash below. Their reddish color comes from the excitation of nitrogen molecules at high altitude, similar to the process that creates the red in auroras. Sprites take many forms, from jellyfish-like shapes with tendrils reaching down to carrot-like columns that stretch toward space. They are best observed from aircraft or high-altitude balloons looking down on storms from above, though they can sometimes be seen from the ground against a dark sky. The discovery of sprites revealed that thunderstorms reach far higher than anyone had imagined. Blue jets shoot lightning upward into space. While most lightning travels between clouds or from cloud to ground, blue jets are electrical discharges that shoot upward from the tops of thunderclouds into the stratosphere. Discovered in 1994, blue jets are narrower and bluer than sprites and can extend 15 to 40 kilometers above the storm. Their blue color comes from the ionization of nitrogen molecules at lower altitudes than sprites. Blue jets represent a direct electrical connection between thunderstorms and the ionosphere, challenging the traditional view that lightning was confined to the troposphere. Scientists believe that blue jets are triggered by intense electrical fields at the tops of the most powerful thunderstorms. Their discovery has expanded our understanding of how thunderstorms interact with the upper atmosphere. The skies above thunderclouds are far more electrically active than anyone suspected before modern observation techniques revealed these upward discharges. Weather shifts have ended entire civilizations. Throughout human history, prolonged changes in climate have contributed to the collapse of societies that seemed established and powerful. The sophisticated Bronze Age civilizations of the Eastern Mediterranean may have faltered, in part due to a severe drought that affected the region around 1200 BCE. The ancestral Puebloans of the American Southwest abandoned their elaborate cliff dwellings during a multi-decade drought in the 13th century. More recently, historians have linked weather extremes to political upheavals, revolutions, and mass migrations that reshaped nations and continents. While weather alone rarely causes collapse, it can push stressed societies past the breaking point by disrupting food supplies and sparking conflict over dwindling resources. Understanding how past societies have responded to climate challenges offers lessons for the present. The ruins of great civilizations serve as reminders that no society is immune to the weather's long arm. A single drought may have toppled the Mayan Empire. The collapse of classic Maya civilization, which saw the abandonment of great cities across Central America between the 9th and 10th centuries, has long puzzled archaeologists. Evidence from lake sediments, cave formations, and tree rings now points to a series of severe droughts coinciding with the period of collapse. The Maya depended on seasonal rains to fill reservoirs and grow crops, and multi-year droughts would have caused water shortages and crop failures across the region. The resulting famines likely triggered social unrest, warfare, and the abandonment of cities that could no longer sustain their populations. Not all Maya cities collapsed at the same time or for exactly the same reasons, but drought appears to have been a common thread. The Maya story warns that even sophisticated civilizations with advanced knowledge and technology are vulnerable to prolonged weather extremes. The jungles that swallowed Maya cities grew over the ruins of a drought. Ancient battles were won or lost because of storms. Weather has determined the outcome of military campaigns throughout recorded history, favoring some armies while dooming others. The storm that scattered the Spanish Armada in 1588 saved England from invasion and shifted the balance of power in Europe. Napoleon's invasion of Russia was crushed as much by the brutal winter of 1812 as by Russian resistance, with hundreds of thousands of soldiers perishing from cold and starvation. The weather on D-Day was meticulously forecast because a break in the storms was essential to the success of the Normandy landings. Generals throughout history have studied weather as a factor as important as terrain or troop strength. Fog has concealed retreats and advances alike, while mud has bogged down armies and turned battlefields into death traps. The same atmosphere that brings rain for crops can bring storms that decide the fate of nations. The Little Ice Age froze rivers in the heart of Europe. From roughly the 14th century to the mid-19th century, a period of cooling known as the Little Ice Age brought harsher winters and cooler summers to much of the Northern Hemisphere. The Thames River in London froze solidly enough to hold frost fairs, where citizens walked, skated, and held markets on the ice. Alpine glaciers advanced into valleys, destroying villages that had stood for centuries. Crop failures became more frequent, contributing to famines and social upheavals across Europe. The exact causes of the Little Ice Age remain debated, with volcanic eruptions, reduced solar activity, and changes in ocean circulation all proposed as contributing factors. Paintings from the era show snowy landscapes and frozen canals that seem foreign to those same regions today. The Little Ice Age is a reminder that natural climate variability can measurably alter human life within historical timescales, even before the era of human-caused climate change. Weather balloons can rise higher than Mount Everest. Twice each day, weather services around the world release thousands of radiosondes, small instrument packages carried aloft by balloons that ascend to the edge of space. These balloons typically reach altitudes of 30 kilometers or more before bursting, far higher than the summit of Everest, and into the stratosphere. As they rise, they transmit data about temperature, humidity, pressure, and wind speed back to ground stations. This vertical profile of the atmosphere is essential for weather forecasting, as conditions high above affect the weather that reaches the surface. The data from thousands of balloon launches each day feeds into the computer models that generate weather forecasts. Before satellites, radiosondes were the primary means of observing the upper atmosphere, and they remain important today because they provide highly accurate measurements that satellites cannot match. The simple act of releasing a balloon has become a cornerstone of modern meteorology. Satellites can see hurricanes from space in real time. Weather satellites orbit Earth continuously, providing images and data that allow meteorologists to track storms from birth to dissipation. Geostationary satellites hover over fixed points on the equator, watching the same region of Earth constantly and capturing images every few minutes. Polar orbiting satellites pass over the entire planet twice daily, gathering detailed measurements of temperature, moisture, and cloud properties. The ability to see a hurricane's spiral bands from space transformed forecasting, giving days of warning that were impossible in the era before satellites. Satellite data is now so routine that we take for granted the ability to watch weather systems develop on our phones. Before the satellite era, hurricanes could appear without warning, killing thousands who had no way of knowing what was approaching. The eyes in the sky have made weather forecasting possible on a global scale. Doppler radar can track raindrops moving through the air. Doppler radar revolutionized severe weather forecasting by allowing meteorologists to measure not just where precipitation is falling, but how fast and in what direction the air carrying it is moving. By analyzing the shift in frequency of radar waves bouncing off raindrops, the same principle that makes a siren sound higher as it approaches, Doppler systems can detect rotation within thunderstorms. This capability makes it possible to identify tornadoes before they touch down, providing crucial extra minutes for people to seek shelter. Networks of Doppler radar stations cover much of the developed world, overlapping to provide continuous coverage of the lower atmosphere. The technology has also been applied to understanding fine-scale wind patterns around airports, improving aviation safety. Without Doppler radar, the tornado warning system would be far less effective. The ability to see the atmosphere in motion has transformed meteorology from observing to truly understanding the air. Supercomputers can model storms days before they form. Modern weather forecasting depends on numerical weather prediction models that simulate the atmosphere using millions of data points and equations that describe how air moves, heats, and carries moisture. The largest weather models run on some of the most powerful supercomputers in the world, performing quadrillions of calculations to produce forecasts extending more than a week into the future. Ensemble forecasting runs multiple simulations with slightly different starting conditions to estimate the range of possible outcomes. The accuracy of weather forecasts has improved dramatically over the past half-century, with today's 5-day forecast as reliable as a 2-day forecast was 40 years ago. Despite these advances, small errors in initial conditions can grow rapidly, limiting how far into the future useful forecasts can extend. Weather models also struggle with phenomena smaller than their grid resolution, which is why local forecasts remain uncertain. The atmosphere is a computer far more complex than any we have built. Weather forecasts today are more accurate than ever in history. Due to advances in observation technology, computing power, and scientific understanding, weather forecasting has improved enormously over the past century. A 7-day forecast today is as reliable as a 3-day forecast was in the 1980s. Tropical cyclone track forecasts have improved even more dramatically, with average errors shrinking by about half every 20 years. This progress has saved countless lives by giving people time to prepare for dangerous weather. The improvement is especially notable for extreme events. where accurate early warnings can mean the difference between evacuation and tragedy. However, forecasts are not perfect and never will be, because the atmosphere is inherently chaotic and sensitive to small uncertainties. Communicating both what is known and what remains uncertain is a challenge that forecasters face daily. The quiet revolution in weather forecasting is one of the great scientific achievements of the past century. The chaos of weather makes perfect prediction impossible. In 1963, meteorologist Edward Lorenz discovered that tiny differences in initial conditions could lead to completely different weather outcomes, a finding now known as the butterfly effect. This sensitivity to initial conditions means that even the most powerful computer, given perfect equations, cannot predict the weather beyond a certain time horizon. The practical limit for deterministic forecasting is about 2 weeks, beyond which forecasts become little better than climatological averages. Ensemble forecasting addresses this limitation by running many slightly different simulations and reporting probabilities rather than certainties. Chaos is not a flaw in forecasting but a fundamental property of the atmosphere that sets limits on what can ever be known in advance. Embracing uncertainty has made weather forecasting more honest and ultimately more useful. The same chaos that limits prediction is what makes weather endlessly surprising and never quite routine. Your joints may ache when atmospheric pressure drops. Many people report that their joints become stiff or painful when a storm approaches, and scientific research suggests there may be a real connection. Falling atmospheric pressure, which typically precedes rain and storms, may allow tissues around joints to expand slightly, putting pressure on nerves and causing discomfort. The effect is most noticeable in people with arthritis or previous joint injuries, whose damaged tissues may be more sensitive to small pressure changes. Some studies have found correlations between weather and joint pain, while others have failed to confirm the link, suggesting that individual sensitivity varies considerably. The belief that weather affects joints is ancient and widespread across cultures, which lends weight to the idea that something real underlies the folklore. Whether or not the pressure change is the direct cause, many people use approaching discomfort as their own personal weather forecast. Your body may be a barometer more sensitive than any instrument. The sky can turn green before a tornado forms. Witnesses to severe thunderstorms sometimes report that the sky takes on an eerie greenish tint in the minutes before a tornado forms. The exact cause of this coloration remains somewhat debated, but the leading explanation involves the interaction of reddish evening sunlight with the blue light scattered by water and ice in a deep thunderstorm. When a powerful supercell contains exceptionally large amounts of water and hail, the blue scattering may combine with red light to produce a greenish hue. Not all tornadic storms produce green skies, and not all green skies indicate tornadoes, but the connection is strong enough that meteorologists take the phenomenon seriously. Experienced storm watchers treat a green sky as a warning sign that severe weather may be imminent. The strange light creates an atmospheric tension that matches the meteorological danger. If the sky turns green and the air grows suddenly still, it may be time to seek shelter immediately. Air pollution can make sunsets burn with deeper colors. The brilliant oranges and reds of a vivid sunset are caused by sunlight traveling a longer path through the atmosphere, which scatters away blue and green light while allowing the longer wavelengths to reach the observer. Particles in the air, whether from dust, volcanic ash, or pollution, can enhance this effect by scattering additional light and deepening the colors. After major volcanic eruptions, sunsets around the world have been famously spectacular, as ash circulates through the stratosphere. Urban areas with significant air pollution, often experience remarkably colorful sunsets for similar reasons. While the visual effect may be beautiful, it serves as a reminder that the air contains substances that affect not just the sky, but also human health. Clean air produces subtler sunsets, while polluted air paints the evening sky in exaggerated hues. The trade-off between beauty and breathability is a strange bargain offered by the atmosphere. Clouds can be seeded with particles to encourage rain. Cloud seeding is the practice of introducing substances like silver iodide or salt into clouds to encourage the formation of ice crystals or water droplets, with the goal of increasing precipitation. The technique has been used since the 1940s, particularly in drought-prone regions and areas dependent on snowpack for water supplies. Scientific evidence for its effectiveness remains mixed, with some studies suggesting modest increases in precipitation, while others find little measurable effect. Part of the difficulty lies in proving that rain fell because of seeding, rather than because it would have fallen anyway. Several countries maintain active cloud seeding programs despite the uncertainty, hoping that even small increases in water supply justify the expense. Critics worry about unintended consequences, including the possibility that seeding might reduce rainfall elsewhere. Cloud seeding represents humanity's first tentative attempts to engineer the weather, with results that remain frustratingly difficult to verify. Red skies in the evening often do predict fair weather. The old saying that a red sky at night is a shepherd's delight, and a red sky in morning a shepherd's warning, reflects a genuine meteorological pattern in many parts of the world. In the mid-latitudes, where weather systems typically move from west to east, a red sunset indicates that the setting sun is illuminating clear skies to the west, suggesting that fair weather is approaching. A red sky at sunrise means the clear air has already passed, and clouds may be moving in from the west. The colors result from sunlight passing through a long path of atmosphere, with dust and moisture scattering shorter wavelengths and leaving the longer red wavelengths to paint the sky. While this rule is not infallible and works better in some regions than others, it reflects real patterns in weather movement. Ancient observers developed such rules long before modern forecasting, building practical wisdom from careful attention. The sky itself has always been humanity's first weather forecast. Climate change is making extreme weather more common. Scientific observations from around the world indicate that many types of extreme weather are becoming more frequent and intense as the global climate warms. Heat waves are occurring more often and reaching higher temperatures, while heavy precipitation events are becoming more intense as a warmer atmosphere holds more moisture. The connection between climate change and individual weather events is complex, but the overall pattern is unmistakable. The dice are now loaded toward extremes. Attribution science has developed methods to estimate how much more likely specific events have become due to human-caused warming. What was once a once-in-a-century heat wave may now occur once every decade or two. The costs of extreme weather, measured in lives and economic damage, are rising as the climate continues to change. Preparing for more frequent extremes has become essential for communities around the world. Storm surges are rising with the seas. Coastal flooding during storms is becoming more severe as sea levels rise, adding height to the storm surges that hurricanes and other coastal storms push ashore. Even small increases in sea level can dramatically increase the area affected by flooding, especially in flat coastal regions. Communities that were once safe from all but the most extreme storm surges now find themselves vulnerable during more ordinary storms. The combination of stronger storms and higher seas creates a compounding risk that threatens coastal populations worldwide. Many of the world's largest cities are built on coasts or river deltas that are particularly exposed to this rising danger. Adapting to increased storm surge risk requires difficult decisions about building, retreating, or defending ever more vulnerable shorelines. The waters are rising, and the storms that drive them inland are not getting weaker. Heat waves are growing hotter and longer. Climate data from recent decades shows that heat waves are becoming more frequent, lasting longer, and reaching higher temperatures in many parts of the world. The record-breaking heat events that once occurred perhaps once in a generation are now occurring multiple times in a decade. Heat waves are particularly dangerous because their slow-building nature gives a false sense of security, while their effects accumulate over days, stressing infrastructure and exhausting human resilience. The urban heat island effect means that cities suffer most during heat waves, with nighttime temperatures remaining high and offering little relief. Vulnerable populations, including the elderly, the very young, and those with chronic health conditions, face the greatest risks. Climate projections suggest that even current warming commitments will produce substantially more frequent extreme heat in the coming decades. Learning to survive increasingly hostile summers is becoming a necessity for communities that once rarely experienced such conditions. Rainfall patterns are shifting across the globe. Climate change is not just making the world warmer, it is redistributing precipitation in ways that create new droughts in some regions while intensifying flooding in others. The general pattern is that wet regions are becoming wetter, while dry regions become drier, though local effects can be more complex. Changes in atmospheric circulation are shifting the paths of storms and altering the timing of monsoons that billions of people depend on. Agricultural systems built around historical rainfall patterns are being stressed by changes that arrive faster than crops and farming practices can adapt. Water managers face growing challenges as the patterns they planned around no longer hold. Some regions are experiencing both more intense droughts and more intense floods, as rainfall comes in more concentrated bursts rather than steady nourishment. The reliable rhythms of precipitation that civilizations were built around are changing in ways that demand adaptation. Lightning strikes may increase as the climate warms. Research suggests that lightning activity could increase significantly as the atmosphere warms, with some estimates predicting roughly 12% more lightning for each degree of warming. Warmer temperatures increase atmospheric instability and the amount of moisture available for thunderstorms, both of which favor lightning production. More frequent lightning would mean more wildfire ignitions, especially in dry regions where fire risk is already increasing. The infrastructure damage from lightning strikes, which already costs billions annually, could grow alongside increased activity. However, the relationship between climate and lightning remains an active area of research, with significant uncertainty about how different types of thunderstorms will respond to changing conditions. Observations of lightning trends over recent decades show complex patterns that scientists are still working to understand. If lightning does increase as projected, it will add another dimension to the challenges of a warming world. Hurricanes are expected to grow stronger in the future. Climate science suggests that while the total number of hurricanes may not increase, the proportion of the most intense storms, Category 4 and Category 5, is likely to grow as the oceans warm. Warmer ocean water provides more energy to fuel hurricane intensification, potentially leading to more rapid strengthening events that catch forecasters and communities off guard. Sea level rise compounds the danger by making storm surges from these stronger hurricanes even more destructive. Some evidence suggests that hurricanes may also be moving more slowly as overall atmospheric circulation patterns change, allowing them to drop more rain over affected areas. The combination of stronger winds, higher surge, and more rainfall makes future hurricanes a greater threat to coastal populations. Preparing for hurricanes that exceed historical experience requires rethinking building codes, emergency planning, and coastal development. The storms of tomorrow may be fiercer than any in living memory. Jupiter's Great Red Spot has raged for centuries without end. The most famous storm in the solar system is a giant anticyclone on Jupiter that has been observed continuously since at least the 17th century. This massive storm is so large that Earth could fit inside it more than once, and its winds at the edges reach speeds of several hundred kilometers per hour. Unlike earthly storms, which dissipate within days or weeks, the Great Red Spot persists because it draws energy from Jupiter's powerful internal heat and the shearing winds of adjacent atmospheric bands. Observations suggest that the spot has been shrinking in recent decades, leading to speculation about whether it might eventually disappear or simply transition to a new stable configuration. The storm's reddish color comes from complex organic compounds created by sunlight acting on the atmosphere, though the exact chemistry remains uncertain. The Great Red Spot is a laboratory for understanding how storms can sustain themselves for far longer than anything possible on Earth. Jupiter's weather operates on scales that dwarf anything in human experience. Saturn's hexagonal storm spins perfectly around its pole. At Saturn's North Pole, one of the strangest atmospheric phenomena in the solar system rotates with precise regularity, a massive hexagonal jet stream that has persisted for at least 40 years. Each side of the hexagon is longer than Earth's diameter, and the pattern rotates roughly every 10 hours along with Saturn itself. Scientists believe the shape arises naturally from the physics of rotating fluid flows, but reproducing it in laboratory experiments remains challenging. At the center of the hexagon sits a hurricane-like vortex with an eye dozens of times larger than any earthly hurricane. Saturn's hexagon was first observed by the Voyager spacecraft in the 1980s and has been studied intensively by the Cassini mission. The regularity and persistence of this geometric pattern challenges our understanding of atmospheric dynamics. Saturn's skies are decorated by shapes that seem almost artificial in their precision. Uranus has winds faster than the speed of sound on Earth. Despite its cold, distant position in the outer solar system, Uranus possesses surprisingly violent weather, with wind speeds that can exceed 900 kilometers per hour. These supersonic winds are driven by internal heat and the planet's unusual tilt, which causes extreme seasonal variations as each pole spends decades in continuous sunlight or darkness. Cloud features observed by telescopes reveal a dynamic atmosphere far more active than its bland appearance in early images suggested. Uranus experiences storms that can rival Jupiter's in intensity, though they are harder to observe due to the planet's distance. The atmosphere is composed mainly of hydrogen and helium with traces of methane, which gives the planet its distinctive blue-green color. Scientists are still working to understand how such cold temperatures can produce such energetic weather systems. Uranus is a reminder that extreme weather can occur even in the coldest reaches of the solar system. Neptune's dark storms are supersonic hurricanes. Neptune, the most distant major planet from the Sun, hosts some of the most violent weather anywhere in the solar system. The planet's Great Dark Spot, observed by Voyager 2 in 1989, was an Earth-sized storm with winds exceeding 2,000 kilometers per hour, far faster than any winds on Earth or even Jupiter. Unlike Jupiter's persistent Great Red Spot, Neptune's dark storms seem to form, persist for years, and then fade away, with new ones appearing elsewhere on the planet. What drives such extreme winds on a planet receiving so little solar energy remains somewhat mysterious, though internal heat released from Neptune's core is thought to play a crucial role. The planet's deep blue color comes from methane absorbing red light, creating an appearance of serene beauty that belies the fury hidden within. Neptune's storms demonstrate that distance from the Sun does not mean quiet skies. Some of the most extreme weather in our solar system occurs in its coldest, darkest corners. Some exoplanets may rain glass sideways at supersonic speeds. Observations of distant worlds orbiting other stars have revealed weather conditions that make even the most extreme Earth weather seem gentle by comparison. Hot Jupiters, gas giants orbiting very close to their stars, are blasted with such intense radiation that their atmospheres are superheated on one side while remaining cooler on the other. This extreme temperature difference can drive winds of thousands of kilometers per hour that carry particles, including molten silicates, that condense into tiny glass droplets horizontally across the planet. The exoplanet HD 189733b appears to be one such world, with blue color possibly arising from silicate particles raining through its atmosphere. Tidally locked worlds which never turn rotation to their stars may have equally strange weather patterns as heat flows from the eternal day side to the eternal night side. The universe of exoplanets offers an almost unlimited range of atmospheric conditions. Weather on Earth is fierce, but it is tame compared to what exists among the stars. Other distant worlds may have clouds made of molten iron. In the most extreme exoplanets, conditions become so foreign that even the concept of clouds takes on new meaning. Some brown dwarfs and hot exoplanets have atmospheres hot enough that iron exists as a vapor, which can condense into clouds of molten metal droplets. These iron clouds would rain liquid metal that falls into even hotter depths before evaporating and rising to condense again. Other exotic clouds proposed for distant worlds include clouds of salt, corundum, and even titanium oxide. The study of exoplanet atmospheres is a rapidly advancing field, with new telescopes able to detect the chemical signatures of these alien skies. Each new observation reveals weather patterns that challenge assumptions developed from studying only our solar system. The atmospheres of distant worlds are laboratories for the full range of physics and chemistry that atmospheres can contain. Earth's atmosphere once glowed orange after its birth. In the earliest days of our planet, before life had a chance to transform the air, the atmosphere was dramatically different from the one we breathe today. Volcanic outgassing filled the sky with carbon dioxide, water vapor, and sulfur compounds that would be toxic to modern life. The sky may have glowed orange or reddish under the young, fierce sun, with no free oxygen to create the blue color we now take for granted. It took billions of years and the evolution of photosynthetic life to gradually fill the atmosphere with oxygen and clear it of the primordial haze. The oxygen we breathe is a gift from ancient organisms that transformed the atmosphere from a toxic shroud into a life-supporting blanket. Every breath connects us to this long history of atmospheric evolution. The blue sky above is a relatively recent development in Earth's long history. The most powerful storm ever measured was here on Earth. Despite the immense storms found on giant planets, some of the most intense atmospheric phenomena in the solar system occur right here on Earth. The fastest winds ever recorded on any planet's surface were measured during a tornado in Oklahoma, with speeds exceeding 400 kilometers per hour. The energy released by hurricanes and the electrical activity of major thunderstorms are among the most powerful natural phenomena anywhere. Earth's position in the solar system, with liquid water, strong solar heating, and significant temperature contrasts between equator and poles, creates conditions for truly extreme weather. Our planet's atmosphere is more dynamic and varied than those of worlds either closer or farther from the Sun. The diversity of weather on Earth, from gentle drizzle to city-destroying hurricanes, encompasses a remarkable range of atmospheric behavior. We live on a world renowned throughout the solar system for its weather. Floods and droughts may alternate more often in the future. Climate projections suggest that many regions will experience an intensification of both wet and dry extremes as global warming continues. The same physics that makes heavy rain events more intense also intensifies droughts when conditions prevent moisture from reaching a region. This whiplash between wet and dry creates challenges for water management, agriculture, and infrastructure that were not designed for such extremes. Some regions have already begun experiencing this pattern, with devastating droughts followed by catastrophic floods in rapid succession. The concept of normal weather is becoming less meaningful as the climate shifts to a new, more variable state. Adapting to this new reality requires flexibility and resilience in systems that were built for stability. The rhythms of water that civilizations grew up within are changing, demanding new approaches to living with the atmosphere. Weather is Earth's heartbeat, always shifting, never still. The atmosphere is in constant motion, a fluid envelope surrounding our planet that never rests and never ceases changing. Weather is not an occasional disturbance but the normal state of a dynamic system, driven by the sun's energy and shaped by geography, rotation, and the properties of air and water. Every day brings new patterns of clouds, wind, and precipitation that are unique in the history of the planet and will never repeat exactly. This endless variety is part of what makes Earth a living world, with weather patterns that have shaped evolution, guided migrations, and influenced human history. The restless atmosphere distributes heat from equator to pole, carries water from ocean to land, and constantly responds to changes in the conditions that drive it. Understanding weather is understanding a process, not a thing, a never-ending story written in clouds and wind. As long as the sun shines and the earth turns, weather will continue its ancient dance. And now the quiet wonders of weather begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the atmosphere. From clouds that weigh more than mountains, to lightning that burns hotter than stars. From hurricanes that carry the energy of nations, to gentle raindrops that fall in perfect shapes no one ever sees. You have explored the frozen hearts of glaciers, walked through storms that rage for centuries on distant worlds, and discovered how weather has shaped the rise and fall of civilizations. You have seen the sky turn green before tornadoes, watched ships float in mirages, and learned how monarch's butterflies ride the winds across entire continents. You are part of this story, not just an observer, but a participant woven into the fabric of the atmosphere. The rain that falls tonight has cycled through oceans and rivers for billions of years. The air you breathe has been stirred by storms across every continent. The very water in your body was once clouds, was once snow, was once the mist rising from ancient seas. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle pulse of rain on a quiet roof, like the slow turning of clouds across the evening sky. Tonight, as you rest, weather continues its quiet work. Clouds are forming, winds are shifting, somewhere in the darkness, rain is falling on distant hills, and lightning is flickering silently on the horizon. The atmosphere never sleeps. You are a small, warm presence within this vast living system, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that weather is the heartbeat of our planet, always shifting, always renewing, and that you are part of its ancient rhythm, connected to every storm and every calm that has ever been. Thank you for joining me on this journey through the world's weather. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of our remarkable planet. There are more wonders waiting, more secrets hidden in clouds and currents, more mysteries to drift through on quiet evenings. Rest well, and may the gentle rhythm of the sky keep you company through the night. This has been Drowsy Discovery. Good night.